Welcome to another video from Biology. This video I want to talk about this paper, Multi-Grain Vision Language Pre-training, Aligning Text with Visual Concept. This paper and its architecture is famous as XVLM, and there is also XVLM v2 recently. So I thought it would be interesting to talk about this paper. Maybe we can also walk through the code, and let's start with the abstract. Most existing methods in vision language pre-training rely on object-centric feature extracted through object detection and make fine-grained alignments between the extracted features and text. It is challenging for these methods to learn relation among multiple objects. So let me explain what's happening here. The final goal of this paper and this architecture, XVLM, is to have a multi-grain vision language pre-training, as the name of the as the title of the paper is. And multi-grain vision language is that when I have a text and I have an image and that text is describing a specific detail on that image, that's why it's called grained. So we want to find that specific detail from that image using that text. It can be multi because in the text we can have like multi purpose, or we need to detect multi-object. And that's why it's called multi-grain vision language pre-training. So it is grained, going to the level of details, and also it is multi, and it is combination of vision and language. As an example, you can say a man wearing a backpack is crossing the street, something like that, with silver backpack, something like that. So first of all, these model can be used in different way, like describing this image, or maybe we have the text and we want to detect the object. So that can be used in different downstream tasks. So for detecting this, previous method come and detect all of the possible objects in the image. For example, a man, a backpack, the car, buildings, street, and others. And then they calculate some features, like the embedding from these images and those objects, and then aligning those texts. For example, a backpack, for example, look at the clip method. So a backpack should be close to the backpack objects here. So that would be some sort of aligning. But the problem is, it said it is challenging to learn relation among multiple objects. For example, the man is wearing the backpack. Maybe the backpack is somewhere else, is on the car, is somewhere else. Um, so creating this connection, it's something interesting, and it's also working with multiple objects is also interesting because, for example, in clip, usually have a text description that describes the image, but it is not fine-grained. In this kind of model, we can go through the details of the image and text. So here they mentioned we propose a new method called XVLM perform uh, to perform multi-grain vision language pre-training. The key to learning multi-grain alignment is to locate visual concept in the image given the associated text, and in the meantime align the text with the visual concept, where the alignments are in multi-granularity. Experimental results show that XVLM effectively leverage the learned multi-grain alignment to many downstream vision tasks and consistently outperforms the state-of-the-art method. So that's the goal of this paper. And how they are describing that, in the introduction, they're just talking about like different models exist for the object detection. People use blah, blah, blah. And then they mentioned that they want to have vision language model to learn multi-grain alignment between vision and language, as it's explained in the abstract. And it said, unfortunately, existing method cannot handle multi-grained alignment between vision and language. And in this paper, we propose performing multi-grain vision language pre-training by aligning text description with the corresponding visual concepts in image. Taking figure 1 as an example, we have the following data for training. The image caption description, the whole image. Let me go up. We have the image caption, and then we have the following data, image caption, region annotation such as man wearing a backpack, each of which has been related to a region in the image, which previous approach roughly aligned the region description with the whole image. And third, Object labels such as backpack, which are utilized by previous method to train object detectors. We reformulate the data so that an image may have multiple bounding boxes and a text is directly associated with the visual concept in each box. The visual concept may be an object, a region, or image itself. As an example, in figure 1, by doing so, our approach learns unlimited visual concept associated with the diverse text description. So the whole idea is that, so when we have a long text, we can segment those texts to have a different like concept in it, and also segment those part of the image. So it's not like working like object detection that you have object detection and then matching those with the text. I will go to the architecture soon. It is somehow a real vision language pre-training model. We do not apply like a step by step or using different methodology and combine them to make this happen like Bleep V2 that use bootstrapping the representation of vision and language. This is completely different training from scratch. So they mentioned here, so the method consists of an image encoder that produces representation of visual concept, including the image itself, a text encoder, and a cross-modal encoder that conduct cross-attention between the vision and language feature. The key to the learning multi-grain alignment is to optimize XVLM by locating visual concept in the image given associated text by a combination of box regression loss and intersection over union loss. This is very interesting fact. So, for example, if you look at the bleep, I can say bleep is a simpler version of the XVLM. So we have the whole text and the text description, but here they are applying a combination of box regression loss and intersection over union for extracting the embedding of the image or locating the visual concept. And in the meantime, aligning the text with the visual concept by contrastive loss, a matching loss, and a mass language modeling loss. So three different loss are defined here. Contrastive loss, a matching loss, and mask language modeling loss. In fine-tuning and inference, XVLM can leverage the learned multigrain alignment to perform downstream vision and language tasks without bounding box annotation in the input images, which is really cool. They're also mentioning that it outperformed previous method like WinVL, which is based on object-centric feature, achieving about 4.6% in terms of R and 1 score on COCO dataset, Microsoft COCO dataset, and XVLM also at, I don't know, this is MS related to Microsoft, I think MS COCO. And also it outperformed Align, Albef. Some of these are in Hugging Face, I've seen them, and Meter by a large margin even though they are pre-trained on more data or have more parameters. On visual reasoning task, XVLM would improve about 0.8 on VQA and 1.06 on NLVR2 compared to WinVL. And it also outperforms SIM-VLM base, pre-trained with 1.8 billion in-house data, especially on NLVR2 by 2.4%. And also on RefCoco. RefCoco Plus is, I think it's the most relevant data for training these multi-grained vision language models. And it could achieve absolute improvement of 4.5% compared to the Uniter and 1.1% compared to MDTR, which is specialized for grounding tasks. And XVLM also has comparable performance with SimVLM in the image captioning generation task. So the contribution is threefold. We propose performing multi-grain vision language pre-training to handle the alignment between text and visual concept. We propose to optimize XVLM by locating visual concept in the image given the associated text and in the meantime aligning the text with the visual concept where the alignments are in multi-granularity. We empirically verify our approach effectively leverage to learn multi-grain alignment in fine-tuning. VLM consistently outperforms existing state-of-the-art method on many downstream vision language tasks. So I don't want to go to the uh, background of this work, but look at this, the architecture. So they have a vision transformer, and we know that for vision transformer, we have to patch images. And then we apply that to the vision transformer. And also average pool D, which is a representation of the whole image, and a reshape of the embedding here. This is the whole image, and this is the different part of the image. So it's mentioning here. So we have I, then we have V1, V2, V3. These are um, like different bounding boxes over here. Yeah. And then we have a text encoder similarly. So we have the whole text encoding, then part of it, different part of the text. For example, the whole text is man wearing a backpack is, etc. And then in text one, which is text one here, we have man crossing the street, man crossing the street. Then in text two, man wearing a backpack. So we have this one, then silver backpack. So we have all of the different features that exist here. So we have, for example, we know this is for training. So we already have the bounding boxes, yeah. So for these boxes, we know what is the representation for the image. For other boxes, we know what is the representation for that. For text also, we know what are the different concepts in the text. So we have these vector and these vector. And between these two, we are applying contrastive learning. This is one of the laws that we apply. And then these are three different things that we wanna have. First is the mask language modeling. Another one is the matching, and another one is the regression on the bounding boxes. We have the MLP head. So how we want to calculate that is, so we get the whole image for the bounding box prediction. We got the whole image, and we just apply the cross attention between the embedding of the text, the whole text, and different part of the text with the image, and we use those information. And also we have a self attention on the text, and we use those information just for regression on the bounding boxes. So that would be the loss, one of the loss. Another loss is we get the image, and also we get all the texts, the embedding, of course, and we apply the cross attention between these and self attention on the text itself to calculate the matching. So which one is matching with which one, and also masking some of these, some sort of uh, BERT that we mask some of the tokens here, or it can be from image, or it can be from text, both. And we just try to predict the next token like in autoregressive way. So we have the language model head there. That's the whole architecture. So we have an image, we have a text, and we have a specific part of the image and a specific part of the text. Some images we don't have any text for them, and for some images we do not have a bounding box. So in some cases, n would be 0. We don't have any bounding box for them. So for at size, they try 32 by 32, and but depend on how many objects we have, we will create n plus 1, because 1 is for the whole image and this for the different bounding boxes that we have. And we get the patches somehow that, for example, let's look at this image. So if we have this, so we will get the whole representation of all of these boxes that there is an intersection between them. So for bounding box prediction, it's like a MLP layer, and we have the hidden representation that we had here, the X1. This is the output here. So we apply the MLP head, and then we apply the sigmoid, and then we will have the bounding boxes. And bounding boxes defined as center X, center Y, and width and height. So because we have different scale for large and small bounding boxes, so they use a linear combination of L1 loss and the generalized intersection over union. And that's why here you'll see that we have that previous loss and also the intersection over union. And we also talked about the contrastive learning loss. So contrastive learning loss is very simple. We predict visual concept and text pair like V and T from batch negatives. Visual concept include object, region, and images, and they randomly sample a mini batch of n pairs and calculate the in-batch vision to text similarity and text to vision similarity. So when we have a pair of V and T, T is a positive example for V, and we treat the other n-1 text within the mini batch as a negative example. So we define cosine similarity, and WCLS is the output embedding of the text encoder. GV and GW are transformers that map the CLS embedding to the normalized lower dimensional representation. So uh, there are also twofold. One is similarity between vision and text, and similarity between text and vision. And for that, they use the cross entropy loss for that contrastive learning. That's the whole purpose of the contrastive learning. So if you go back here for that contrastive learning, when we say this V1 shouldn't be close to T2, for example, so that contrastive loss is not only for making this representation close for T1 and V2, is also useful for making more discrimination between V1 and T2 and T3 and vice versa. So we have different combination there. And then we have matching prediction. And for matching, they mentioned here, for each visual concept in the mini batch, we sample an in-batch hard negative text by following key vision to text in equation 3. So they use a similar batch, and this time for the one that they are related to each other, they're using the matching loss. So these should match together, like these T1 and V1 should be matched together, and so on. So, and for mask language modeling, they said they randomly mask out the input token with probability of 25% and the replacement on 10% random tokens, 10% on change, and 80% mask. They use cross-model encoder outputs and append a linear layer followed by softmax to predict for prediction. And so it means that they haven't masked the vision, they just mask the text. And they also mentioning here that they use 8 800 GPUs, and the batch size is set to 1024 and training is for 200K step. That's a long training in the about 3.5 days. They use Adam weighted, and these are the parameters that they training. At the end, they are comparing this with different methods like Uniter. This is also a very cool paper. If you have time, you can look at this paper too. But comparing to the other methods, like 16 million XVLM is outperforming even a 1.8 billion SIM VLM. And of course, it's also mentioning that some of these methods are trained on a very larger dataset. And it is outperforming in many datasets like visual question answering, RefCoco Plus, which is the multi-grain vision language, and Coco Caption, which is very similar to the Blip. And let's see some of the output of this. The text is pot behind dog. So when we say dog and we are showing the GradCam visualization of bounding box prediction on unseen images, which is very cool because when you say dog, it can detect it. When you say behind, because I think it has some concept of behind dog, it can understand what is behind dog, and then pot. So we have a pot here, and also I can see some sort of pot also here. Another one is this one. It's saying person eating pizza on poster. Person. This is surprising that he's not catching this because this man is not eating pizza. So person is this one eating at his mouth, and pizza. Look at the pizza, whole pizza, and poster. The whole thing is detected as poster. This is really amazing. And in the same text, if you ask man not on poster, detect that box. If you show that bounding box, if you say just man, so it detects this man. Person eating pizza, person not eating pizza. So you can ask different questions. Of course, these are not seen data. These are not passed to this for training. So this is really cool that you can ask any visual question, and those questions can be showing the interaction between the object, like pizza and the man, and process of eating is also somehow captured by the model. Let's go to the code. Let me see what we have in the appendix. We have, yeah, you see that it is also compared with leap method and also the align. And it is really outperforming that. Of course, number of parameters is more than clip, less than align, but the performance is much better. So what I want to do is now, if I go here and search for XVLM, let me see what we are getting here. So we have a GitHub repository here. And here they are also mentioning X2VLM is also published, as I said, in November 2022. And I don't want to go through this paper. There are some changes they applied on this one. And XVLM2, you see that some of the figures are just repeated. Instead of contrastive loss here, maybe they apply something different. You see many of the formulation are just repeated. In comparison, you can see that in some cases they are getting a little better comparing to the previous methods. I don't want to go through this paper, but you can look at this paper as the future work that you want to do. What we want to do now is also look at this, like modal, cross-modal retrieval on Coco. I like to see this visual grounding on RefCoco one, which is currently, this is in rank 5. When I was reading that paper, it was not rank 5. You can see XVLM is number 2. There is another model like 3% better, mplug 2. I haven't seen that too. Code is not available for this method yet for ICML 2023, which is interesting. But the whole topic is really interesting for me because I think this is the future of AI, the multimodal, is fine-grained, uh, multi granularity object detection or interaction of the text and image. This is awesome. And they also mentioning it can work with image, video, plus transfer to other languages and domain, which is cool. So let's see how we can use this code. Data set is a little tricky because you need to look at the Coco format. For example, I mean Coco Ref Coco Plus format, better say. So in Ref Coco Plus format, there are objects like Coco format, and there are also text description of those objects itself. So here is mentioning the checkpoints and others. XVLM class is coming from models, model VQA, import XVLM. This is just for VQA, visual question answering. But let's go inside that. I think that would be cool. So it was in models. Okay. Models VQA, model retrieval, model pre-train. Yeah, different things. Model bounding box. Let's see VQA. Okay, we have XVLM base also. Let's go to the XVLM base because the base should be same. And then on top of that, we should have other. Yeah, so the code is available. We don't need to write it, but let's see XVLM base. Oh, so you can see that. Let me zoom in a little bit. So you see in XVLM base, we have built vision encoder and built text encoder. Let's go to the build vision encoder. And what we are getting here is it just use clip VIT. We can also use swing. In the configuration, we can say we're going to use swing transformer or VIT. Set burst and clip and swing with comments. And it just returned this. So any vision transformer, I think we can use that from Hugging Face. It's also using it from Hugging Face. Yeah. Image models VIT vision transformers. So it should have models VIT. Oh yeah, it's using TIM and it's creating those models itself. So we have all models here like MLP, blocks, attention layer, vision transformers. Yeah. So let's back to that XVLM and XVLM base. And we get this vision transformer and then we go to the text encoder. And for text encoder, it's just using, for example, Roberta masked, or we can use also BERT. Oh, so we have the text encoder. And these all also use X-Roberta. Yeah, they have written everything from scratch. They could use something like transformers, but they did it themselves, which is cool. Oh yeah, they use transformers. If we go back to this, let's see what happened after we get this. So we have the vision transformer, text encoder, vision encoder, and here the definition of the contrastive loss, matching loss, and box loss. So we will have that MLP sigmoid layer. On top of that should be matching loss, again another MLP. Oh yeah, and we have the contrastive loss applied a linear layer, get the projection of the text and vision. We have also get contrastive loss, so we pass an image feature and text feature. It will calculate contrastive loss. Yeah, text to image and image to text using the cross entropy loss, matching loss, and this is really cool. MLM loss. Yeah, that's the sigmoid part. Because XVLM now I think it's being used in, for example, in VQA, model VQA. So it's importing, yeah, here, and then we have the forward function here. We have load pretrain forward function here. So we get an image and we get the embedding for that image. So then we pass it to the text encoder and we get image encoder attention mask. And this is just torch one. So this is image attention. Which part of the image we need to put attention, which would be all of the image. And we use that for just image attention. And we have the image embedding, and we get that question. So in the forward function, we get image and our question. And for training, we use the answer. What is the K? Maybe how many beam search we have? Yeah, we will find out. And we will get the input IDs, the attention mask of the question, and for the image, we have a text encoder, and we get question output. And yeah, that would be for the beam search for the ranking answer. How many answers we want to get, top how many, top K IDs. And then we have the rank answer. And for rank answer, we decode the image, decode the text, and we get the probabilities, and at the end we should rank them. But that answer, visual question answering, is not like returning a bounding box, because at the end, what we are getting out of the question answering is just a text, I think. What others we have is model bounding box. If we look at that, we get output coordinate, loss of the bounding box. So these kind of models, like we have image and we have a text IDs, and then we want to get the target bounding box. So we have an image, we ask some question, we want to just get bounding box of those images, like we show in the paper. Another kind of model is model captioning. So in the forward function, again, if we look at that, I think these kind of thing maybe have a generate, yeah, also have a caption here. So image captioning, we get image and caption, and for generate, yeah, for generate, we want to generate a caption. Yeah, so we get caption. Get caption we have as an output. I think we will generate the caption, and if we look at the get caption function, you will see that we will decode the output and get the text there. So there are other things like model retrieval that the forward function is. In this case, it's just different loss that we have. Yeah, this is it. I think it would be easy to just load the one of the model, and for the pre-trained weight, oh yeah, and we have the checkpoints. Yeah, that's it. I hope you enjoyed the video. Please subscribe, leave comment, and share with your friends. Have a good day.